Hello, this is Dr. Hanaa Assil, and this is questions and answers on entropy, which is part of Unit 4 for the IA2 Chemistry Edexcel syllabus. So let us take a look at some of the questions. Consider the reaction between solid ammonium carbonate and pure ethanoic acid. The equation for this reaction is this. Predict the sign of the entropy change of the system. Fully justify your answer. Remember, we said delta S of the system should be positive if what happens? If we have solid and liquid forming gases, so that is an increase in entropy, so this means the delta S system is positive. And if we count the number of moles before and after the arrow, we see that a total of 3 moles of reactants gives a total of 4 moles of products. So in these cases, delta S system must be positive. Do we understand that? There's a previous video explaining the basics on entropy. Please refer to it. The equations for dissolving 2 sulfates are shown below. So he gives me dissolving magnesium sulfate and barium sulfate. He says the delta S total for dissolving magnesium sulfate is a positive value. And we said when it is positive, that means it will be feasible or it will happen spontaneously. But the barium sulfate, the delta S total is negative. Now he's saying compare the values of the total entropy changes for dissolving these 2 sulfates and show that they are consistent with the trend in the solubility of the group 2 sulfates. I want to remind you that in A2 you are expected to remember the things we learned in AS. So in AS we talked about solubility of magnesium sulfate and barium sulfate, and we said as we go down the group, the sulfates become less soluble. So the magnesium sulfate will dissolve easily, and this is shown by the delta S total, which is a positive value, while the barium sulfate, going down the group, the barium sulfate is less soluble, and this is indicated by the delta S total, which is a negative value. The values of the total entropy change and the equilibrium constant of a reaction are related by this. I want you to remember these equations. We said we had a series of equations that we needed to learn. One of them says delta S total is R natural log of K, and K here is the equilibrium constant, and R is a constant which is always 8.31. It's the gas constant. So he says calculate the value of K. Now, previously he gave you delta S total. So we have the equation, and he said delta S total is plus 20 joule per mole per Kelvin. The delta S total is equal to R ln K. So ln K will be the delta S total over R. So we use that value of delta S total over the 8.31. This gives me the natural log of K. Now, in order to get K, this is the inverse of the natural log. So K is this one. Do we understand that? So please remember these equations. One of them is delta S total is R ln K. This next question says nitrogen dioxide reacts with carbon monoxide. Calculate the standard entropy change of the system. So we want to calculate delta S system. Again, I want to remind you, how do we calculate delta S system? Delta S system is the entropies of the products minus the entropies of the reactants. So he will always give you the standard molar entropy of each of the species in the reaction. The delta S system is the total of the products. So we have the 210.7 is for the NO, plus the CO2, which is 213.6. The total of that minus the molar entropy of the reactants, the one for NO2 and the one for CO. The overall here is this number. Remember that the unit in this case is joule per mole per degree Kelvin. Then he says, given that delta H for for the reaction between nitrogen dioxide and carbon monoxide is this: calculate the standard entropy change of surroundings. Another equation that you should remember is the fact that delta S of surroundings is minus delta H over T. So the delta S of surroundings, change in entropy of the surroundings, is minus delta H. He gives me delta H is minus 226, so this is minus of a negative number, so my overall answer is positive, over the temperature, which has to be in Kelvin. Usually he gives it to you in Kelvin. If he doesn't, then you should change it to Kelvin by adding 273. So here, this is my answer, and unit of delta H is in kilojoules, so the units here will be in kilojoules per mole per degree Kelvin. Since you can change it to joules by multiplying by 1,000. Then he says calculate the total entropy change. So you should remember that the total entropy change is the sum of the entropy change for the system and the entropy change for the surroundings. We already calculated and previously that the delta S system is this number. Here we calculated the delta S surroundings. We add them up. It comes out to be in this number. Please note that both of them have to be in the same unit. So either both of them are in joule per mole per Kelvin or kilojoule per mole per Kelvin. Again, this next question gives me the Haber process, and he says at 298 the standard entropy change of the system is this. So here he's given me the delta S of the system, and he says calculate the entropy of 1 mole of ammonia. So we have the delta S of the system, which is the entropy of ammonia minus the entropy reactants, minus the entropy of the reactants, and the overall is in joule per degree per mole. The value of the total entropy change varies with temperature. He gives me a table of 1 over T and the delta S total at each temperature. Plot a graph of delta S total against 1 over T and include a line of best fit. So he gives you this. You should be able to plot the readings, draw a line of best fit between the points. Then he says the relationship between delta S total and 1 over T can be found by combining two equations. We already know that delta S total is delta S surroundings plus delta S system, and delta S surroundings is minus delta H over T. So that means that delta S total is that minus delta H over T plus delta S system. So if we have this graph, this is the graph of what? Of delta S total versus 1 over T. So you should realize that if I get the gradient, then the gradient is the minus delta H. So the gradient, we get it in the normal way. This gives me a certain number, and you should realize now he's saying identify the thermodynamic quantity that can be obtained from this gradient. The gradient will be actually minus delta HR, or it will give you the entropy change of reaction. Determine the temperature at which the reaction ceases to be thermodynamically feasible. Remember, a reaction will be no longer feasible if delta S equals 0. So if the delta S total is 0, then or negative, then the reaction is less feasible, or it stops being feasible. So whenever he says something at which the reaction ceases to be feasible, thermodynamically feasible, that means I'm looking at delta S total equal to 0. So where in this graph is delta S total 0? Can you see the red point there? That is at about 0.00215. So that means this is my 1 over temperature, and I can use that to get the temperature at which the reaction ceases to be thermodynamically feasible. Then he says the industrial synthesis of ammonia is this. It is carried out at a pressure of 20,000 kilopascal, temperatures between 700K and 750K. These temperatures are higher than the answer in C3. Can you see the temperature at which the reaction ceases to be feasible? It is at about 465K. So here we're talking about a temperature that is higher than that. State the relationship between total entropy and equilibrium constant. What is the relationship between total entropy and equilibrium constant? You should know this equation. Delta S total is equal to R ln K. Calculate the value of K at this temperature. So we can use that equation. We have already gotten delta S total. We know what is delta S total. We can put it into this equation in order to get the natural log of K, and then inverse of that will give you the value for K. So remember that this is the relationship between delta S total and the equilibrium constant. Explain why delta S total decreases with an increase in temperature. I want you to remember again, what is delta S total? It is the total of the system and the surroundings. The system, delta S system, is not affected by the temperature, but the delta S of the surroundings, we said it is minus delta H over T. And that means if I increase temperature, then this will decrease the delta S surroundings. And as a result of that, the delta S total will also decrease. Are we following? State how the Haber process is made economically feasible. So we realize that at very high temperature, it is not really feasible, but what we do is the unused reactants are recycled to produce more ammonia, and the ammonia is removed as it is full. This other question says the standard enthalpy change of solution for ammonium nitrate is this. So this is the delta H. Calculate the value of the standard entropy change of the surroundings. We said, how do we get surroundings? Do you remember the equation? It's minus delta H over T. So he already gives me the delta H up there, but the delta H has a positive sign. That means my delta S will have a negative sign. So the delta S of the surroundings would have a negative sign. Explain what can be deduced from your answer about the sign of the value of the standard entropy change in the system. We said the delta S total is the system plus the surroundings. If it dissolves, then the delta S total has to be positive. So if the delta S surroundings is negative, that means the delta S system must be positive in order for the overall to be positive. Following? Okay. Then he says potassium bromate decomposes to form potassium bromide and oxygen. The standard molar entropies of these substances are given in the table. I want to draw your attention to the fact that if you're looking at old past papers, they will tell you look up the molar entropies in the data booklet. But for the recent exams, that's not what they do anymore. It is not in the data booklet. It is put for you in the question itself. So you get the standard molar entropies of the substances in the question, as he has here in the table. Then he says, calculate the total entropy change for this reaction at 298. So in order to get delta S total, how do we get delta S total? Delta S total is delta S of the system plus delta S of the surroundings. So I need to get delta S of the system first. How do we get delta S of the system again? The entropies of products minus the entropies of reactants. Please remember that if you have 2 moles of KBr, that means the entropy will be 2 times the KBr, which is 95.9. I have 3 moles of oxygen, that will be 3 times the molar entropy of oxygen. All of this minus 2 times the molar entropy of the KBrO3. The overall here is a positive number. What comes out, of course, is in joules. If you want it in kilojoules, you divide by 1,000. So that is delta S system, but he wants delta S total. So we got the delta S system. We can now get the delta S of the surroundings, which is minus delta H over T. The delta H is up there next to the equation. So it is a negative number, and that means my overall delta S surroundings will be positive. Again, this is in kilojoules because the delta H is in kilojoules. Please pay attention to the units. And that means if I want the delta S total, I just add the two numbers together. They, in this case, come out as a positive number in kilojoule per mole per degree. This question says ammonia is manufactured in the Haber process. In this process, pressures between 100 atm and 300 atm and temperatures between this and that are usually used. He's saying calculate delta S system. Again, how do we calculate delta S system? It is the entropy of products minus reactants. I have 2 of ammonia, that means 2 times 192.3. Minus the reactants, I have 1 of nitrogen and I have 3 of hydrogen. The overall is in joule per mole per degree. In this case, the delta S system is negative. Explain using ideas about this order whether the sign of your answer to A1 is as expected. If you look at the equation for the Haber process, I have 4 moles of gases giving 2 moles of gas. That means I have a decrease in entropy. So when we say delta S of the system is negative, that is correct. It is the sign that is expected because this order decreases since 4 moles of gas give 2 moles. Are we following how to explain your answer? Then he says at 700 K, the enthalpy change for this reaction is this. So he gives me delta H and he says calculate the entropy change of the surroundings. Again, how do we do that? There are just a few equations that you need to remember. What is delta S surrounding? Minus delta H over T. In this case, my delta H is negative, so my overall answer will be a positive number. The T he gives you as 700 K. What you get is in kilojoule per mole. You can then multiply by 1,000 to get it in joule per mole per degree. Then he says at 700 K, the total delta S is minus 78.7. So he's giving me delta S total, and we already calculated delta S surroundings, and he wants delta S of the system. So we know that the delta S total is the sum of system plus surroundings. So I can use that to get the system. It is the delta S total that he gives me minus the delta S surroundings that we calculated, and this comes out to be a negative number. Again, pay attention to the units. Both of them should be in joules per degree per mole or kilojoules per mole per degree. Okay? Then he says, explain one advantage and one disadvantage of using a temperature higher than 700 K in the Haber process. Why do we use a high temperature? Consider the effect of an increase in temperature on. So you have to mention the effect of increase in temperature on the rate, on the values of delta S surroundings and delta S total, and on the equilibrium constant. This question alone has 6 marks. Please pay attention. So the advantage of using a higher temperature is increase in temperature increases the rate. So more ammonia is produced per minute, or the reaction reaches equilibrium faster. But then what is the effect on the values of delta S surroundings and delta S total? We already have delta S total is minus. So the delta S total is a negative number. And we know that delta S surroundings, which is minus delta H over T, this is a positive number. This is what we got. So that means that at higher temperatures, the delta S surroundings will decrease. It will be less positive. And that means the delta S total will be more negative. We will have it, so it will be less and less feasible. Now, the equilibrium constant, we know that delta S total is R ln K. And you should realize that if the delta S total becomes more negative, then the K decreases and the equilibrium moves to the left, and there is lower yield of ammonia that is obtained. Then this question says silicon tetrachloride is used in the manufacture of optical fibers, and he gives me the equation with its delta H. He also gives the molar entropies of the substances involved, and he says calculate the total entropy change for this reaction. Again, how do we get the total? The total means I need to get delta S system, I need to get delta S surroundings, and then add them up. So how do we get delta S system? It is the entropies of products minus reactants. So the entropy of the SiCl4 plus the entropy of CH4 minus that of the reactants. And remember that we have in the reactants 1 of SiC, but we have 4 of HCl, so I have to multiply that number by 4. Overall, the delta S system is this number with a negative sign and joule per mole per degree. Again, do not forget the signs. Whether they are positive or negative, you have to put them. Now, how do we get delta S surroundings? We said delta S surroundings is minus delta H over T. The delta H is up there. It's a negative sign. That means my delta S surroundings will be overall a positive number. This is in kilojoule per mole. Now, when I add them together, I have to make them the same units, either both of them joules or both of them kilojoules. So in this case, I made it both of them joules, and I add the system plus the surroundings, and this comes out to be this number in joule per mole per degree. Okay. Then he says in industry, the reaction is carried out at 700 degrees Celsius. By considering entropy and other relevant factors, justify the use of this temperature. We said, why should I use a high temperature like this? If we have delta S surroundings minus delta H over T, that means at higher temperature, the rate is fast. So this is the advantage of using a high temperature. But then at high temperature, the delta S surrounding is lower, so the delta S total is less positive, so the reaction is less feasible and less yield is obtained. So we just use it to increase the rate. Use your answer from this to calculate the equilibrium constant. That is from the delta S total. He already gave me the delta S total over there. We calculated it actually. Over R, you should remember that R is 8.31. This gives me the natural log of K. If I do the inverse of that, it gives me the equilibrium constant. An airbag is a safety device fitted to modern cars. It is designed to inflate extremely rapidly in the event of a collision. Remember this introduction, just go through very quickly. This is the equation, and he gives me the delta H, and he says predict the sign of the delta S system. Again, how do we know what would be the sign of delta S system? I look at the equation. What do we have in the equation? I have 2 moles of solid gives a total of 5 moles, which includes 3 moles of gas. This is obviously a positive delta S system. We have 2 moles of reactants giving 5 moles of product, and we also have the fact that solids give gases. Then he says, calculate the entropy change of the system. So delta S of the system, we said, how do we do that? If this is the equation, the delta S of the system is the entropies of products minus entropy of reactant. Don't forget to multiply. If we have 2 sodium, you multiply the 1 for sodium by 2. We have what? We have, he gives me the molar entropy of half N2. So I have 3N2, that means I have 6 times that number. These are for the products. Then I subtract the ones for the reactants, which is 2 times the one for sodium azide. So my overall answer is a positive answer in joule per mole per degree. Then he says, calculate the entropy change of the surroundings. Again, how do we get delta S surroundings? We said delta S surroundings has to do with the delta H. So delta S surroundings is minus delta H over T. He gives me the delta H up there as a negative number. So my delta S surroundings is a positive number. It will come out in kilojoule per mole. You can then multiply by 1,000. Now use your answers to calculate the total entropy. Of course, total entropy is the sum of the two entropies that we just got. So that comes out in this number in joule per mole per Kelvin. Okay. The next question says, this question is about the reaction between solid barium hydroxide and solid ammonium chloride. Calculate the standard entropy change for the system. So again, how do we get delta S of the system? He gives me the standard entropy of each of the species. It will be the products minus the reactants. And again, do not forget to multiply. If I have 2 ammonia, that means I have to multiply the one for ammonia by 2 and so on. So this comes out to be my final answer. Please, as you go along, you can stop the video, try calculating it in yourself, and then check if you get the correct answer. Then he says, is the sign for the delta S system as you would expect? Well, we got the delta S positive. Is that reasonable? Let's look at the equation. The equation says we have solids giving gas. Solids giving a gas, that is an increase in entropy, so the delta S of the system should be positive. The number of moles on both sides are the same, so it is because of the formation of the gas. So solids form a gas, so the delta S system is positive. The total standard entropy change is this, so he gives me delta S total. Calculate the delta H. How do we get the delta H? We know that the delta S total is the delta S of the system plus delta S of the surroundings. So I can use that to get the delta S of the surroundings because he gives me the total and we just calculated the system. So my overall, this is my delta S surroundings. Then we use this equation minus delta H over T in order to get delta H. So the delta H will be minus delta S surroundings times T, and this will give me the number for the delta H. But remember that what comes out here will be in joules. You can divide by 1,000 to get it in kilojoules. State and explain how you would expect the temperature to change this reaction. Again, we said the delta H that we got is positive. So the reaction is endothermic, and that means the temperature would decrease. Nitrogen monoxide reacts with oxygen as shown. He gives me the equation and the delta H, and he gives me the standard molar entropy of each species, and he says calculate delta S of the system. Again, how do we calculate delta S of the system? It is the entropy of products minus reactants. So I get this. It comes out in a negative number. Again, please do not forget sign, positive or negative, and the units. The units are in joule, mole to the minus 1, K to the minus 1. Then he says calculate the entropy change of the surroundings and then the total entropy change. So in order to get delta S of the surroundings, how do we get that? We said it's from delta H. Delta S of the surroundings is minus delta H over T. He gave me the delta H in front of the equation. It is a negative number. That means overall my delta S surroundings will come out as a positive number. Here it is in kilojoule per mole. I can then multiply by 1,000 to put it in joule, mole to the minus 1, K to the minus 1. And then I can use that to get the S total. Delta S total is the total of the entropy change for the system plus the entropy change of the surroundings. I put the numbers that we got, and it comes out to be a positive number. Please do not forget to write the sign, whether it's positive or negative. Calculate the temperature at which the reaction ceases to be spontaneous. Again, we said a reaction is not spontaneous when what? when delta S total is 0. So the reaction ceases to be spontaneous when delta S total is 0. So I can use that to get the delta S of the surroundings. Delta S of the surroundings will be the delta S total minus the delta S system, which we calculated previously. So this comes out to be this number. I can use that to get my temperature from the equation of delta S surroundings is minus delta H over T. I can use that to get the T, and the T comes out in Kelvin, of course. Okay. Nitrogen monoxide and carbon monoxide are formed in car engines. To prevent these pollutant gases being released into the atmosphere, car exhausts are fitted, and we have an equation, and he says, at the temperature of the car exhaust, delta S total for this reaction is positive. So just why this reaction needs a catalyst. Of course, we need a catalyst to lower the energy of activation. This question says we have sucrose, chemical commonly known as sugar, and he gives me this values for the entropy changes and the delta H of combustion and so on. And he says calculate the entropy change of the system. Again, from this equation, we calculate the entropy change of the system, products minus reactants. Remember, products, I have 11 of water, so 11 times the entropy of water, plus I have 12 of CO2, so 12 times the entropy of CO2. All of that minus the reactants. The reactants are 1 glucose, that is 392.4, and I have 24 of O2 of oxygen, because the entropy change of oxygen that he gives me is for half O2. I have 12 times 2, that's 24. 24 times the value that he gives me. This comes out to be a positive number in joule, mole to the minus 1, K to the minus. Then he says calculate the delta S surroundings. As we said before, delta S surroundings is minus delta H over T. You put in the value that he gives you for the delta H, which is negative, then overall delta S surroundings is a positive number. Calculate the total delta S. The total delta S is the sum of the system and the surroundings. That comes out to be positive. He says, state the significance of your answer. The delta S is positive, and that means that the reaction is thermodynamically feasible. That is the significance of this number. State and explain the effect, if any, of increasing the temperature on delta S surroundings and delta S total. So you should realize we said delta S surroundings is minus delta H over T, so increase in temperature lowers the delta S of the surroundings. Now the total delta S total, the delta S total will be less positive, but it is still positive, so the reaction is still spontaneous. So this is the end of these questions. Please try solving the questions before looking at the answers, and I hope this will be useful to you. Thank you for listening.